in a previous video, we saw that when we took the dot product of two vectors u and v, that was equal to the magnitude of u times the magnitude of v times the cosine of the angle between u and v. Well, we have a similar property for cross products, and that cross product property is that the magnitude of u cross v is equal to the magnitude of u times the magnitude of v times the sine of the angle between them. So this does not give the cross product vector, but it does give the magnitude of the cross product vector. And this is important when in physics concepts such as torque, where you're trying to find the cross product of two vectors and you want the magnitude of that cross product to calculate torque. So we can prove this property essentially by using properties of the unit vectors. So this can be proven by using the fact that I cross j is k, j cross k is I, and k cross I is j, and then also using the fact that if you cross a vector with itself, then you end up getting 0. That's something that you can verify for yourself if you like, but the cross product of a vector with itself is going to give you 0. If you have those properties, then you can let u equal u1 I hat plus u2 j hat plus u3 k hat, and you can let v be v1 I hat plus v2 j hat plus v3 k hat. And if you then expand the product of u cross v using those properties that I laid out in the previous video, so if you use these properties that I laid out in the previous video, then you will get essentially the magnitude of u times the magnitude of v times sine theta. So that's kind of the method for proving, but it's just a long calculation that you have to chase through. And so I'm not going to go through all of those details. But that is the geometric significance of the cross product. And that gives you the magnitude of u cross v. What you would need to, or what you'd want to know next is the direction of u cross v, if you already knew the magnitude. And the direction of u cross v can always be determined by what is called the right-hand rule. The right-hand rule allows you to take your right hand, point it in the direction of the u vector, curl your fingers in the direction of the v vector, and then your thumb will point in the direction of the result u cross v. That's hard to explain just verbally, so what I'm going to do is link a couple videos that show you how to apply the right-hand rule so that you can see a demonstration of those. So see the linked videos. Okay, now that we have this property of cross products in terms of the magnitudes of u and v and sine theta, okay, we can talk about some corollaries. The first one is that two non-zero vectors u and v are parallel. That means theta is 0 or theta is pi if and only if u cross v is 0. So if we have that u cross v is 0, then we have that the magnitude of u, which is not 0, and the magnitude of v, which is not 0 because they're non-zero vectors, times the sine of theta is equal to 0. Well, that tells me that the sine of theta has to be 0. And so that tells me that theta has to be 0 or pi. And so if you have two parallel vectors, then their cross product is going to be 0. The second corollary of this theorem is that the area of a parallelogram formed by u and v is actually the magnitude of u cross v. So what do I mean? So I'm going to draw a vector. We'll call this vector u. And then I'll draw another vector. We'll call that vector v. And then I'm going to form a parallelogram using those two vectors. This is not unlike the parallelogram that I drew when we were adding two vectors together. So let's pretend that's a nice looking parallelogram. Okay, and I want to find the area of the parallelogram that is formed by those two vectors. And we'll remember that the area of a parallelogram is the base of the parallelogram times the height. So the base of this parallelogram is the magnitude of v. Now I need to draw in the height of the parallelogram. And I'm thinking that there's an angle theta between u and v. And so if this u has a magnitude u there, then the length in red, the height, is actually the magnitude of u times sine of theta. And so we know that the area is then equal to the base times the height. So we have the height, so we have the base, magnitude of v, and then the height is magnitude of u times sine theta. And this can be rewritten as magnitude of u, magnitude of v, sine theta, and by that theorem, that's actually the magnitude of u cross v. So there we have it. The area of the parallelogram formed by u and v is the magnitude of the cross product. We can actually take that one step further with what are called scalar triple products. The scalar triple product is going to be u dot v cross w. So the u dot v cross w, I'm just going to write down what that is first. If you want to take u dot v cross w, if you think about that dot product, this is actually going to be the determinant of the matrix u1, u2, u3, v1, v2, v3, and w1, w2, w3. So I'm doing v cross w, and normally you would have here I, j, and k. But if you think about the fact that u is equal to u1i plus u2j plus u3k, and then you're going to dot that with the I, j, and k that come out of this determinant, then you can go ahead and replace this row with u1, u2, and u3, and you'll have the same result. Okay, so that's called the scalar triple product. That's u dot v cross w. Okay, so the scalar triple product, though, is actually going to give me the volume of something that's called a parallel piped. So what I'm going to do is I'm going to put out 3 vectors here. So I'm going to have my u vector. Sorry, I'm going to have my v vector. And then I'm going to have a w vector. And finally, I'm going to have my u vector. And what a parallelepiped is if you took those 3 vectors and you made a 3-dimensional solid with those vectors. So I'm going to make this v vector just a little bit longer and a little bit shallower here. So with every one of these vectors, I'm going to make a plane that's formed by those vectors. Okay, and then I might need to redraw this just a little bit. So this is the parallelepiped. Okay, and that's basically a 3-dimensional version of a parallelogram. Okay, and so that's the parallelepiped that's formed by V, W, and U. And I want to find the volume of that. So the way that I find the volume of that is I need to find the volume is going to be the height times the base area. And so we have that the height, we can think about as being, if this is an angle theta here, the height is actually equal to the magnitude of u cosine theta. So here we have the magnitude of u here. And then what we're saying is that this height is going to be the magnitude of u times cosine theta. And then the base area, well, the base area we already saw is going to be the magnitude of v times the magnitude of w times the sine of the angle between them. I'm going to give that angle a name phi. So what you can see, though, is that we have a u cosine theta times essentially v cross w, the magnitude of v cross w. And then using our rules for dot products, our interpretation of the dot product, we will see that this is indeed u dot the vector v cross w, because if you do u cross or u dot v cross w, you should get the magnitude of u, the magnitude of v cross w cosine theta. Okay, so let's do an example. We're going to find the scalar triple product of those 3 vectors. They are 2, 0, -3, 1, 1, 1, and 0, 4, -1. That's going to give me 2 times 1, 1, 4, negative 1, that determinant, minus 0 times 1, 1, 0, negative 1, and then plus a negative 3 times a 1, 1, 0, 4. So this is 2 times negative 1 minus 4. And that's going to be minus 3 times 4 minus 0. So this is going to be negative 10 minus 12, or negative 22. And so the volume of the parallelepiped would be the absolute value of that, which is 22. So the volume of the parallelepiped that's formed by those three vectors is going to be 22. Now, we can also use scalar triple products to take 4 points and show that they actually lie in the same plane. So here are these 4 points, A, B, C, and D. And if I look at the vectors A, B, which the vector AB in this case, taking B minus A, is going to be 1, 1, negative 1. The vector AC, that's going to be the point C minus the point A, which is 2, 3, negative 2. And then the point AD, that's going to be 4, 5, negative 4 if we take the point D and we subtract the point A. And if we have these three vectors, we can take the scalar triple product of these three vectors. And if that scalar triple product is 0, then what we have is a parallelepiped that has no height to it. So that means that all three vectors must lie in the same plane, and therefore all 4 points, are coplanar. So we'll do this last computation. We will take this triple product of these three vectors. So 1, 1, negative 1, 2, 3, negative 2, 4, 5, negative 4. So this is equal to 1 times 3, negative 2, 5, negative 4, that determinant, minus 1 times 2, negative 2, 4, negative 4, and then minus 1 times 2, 3, 4, 5. So 3 times a negative 4 is, negative 12 plus 10. Minus 1 times, this looks like negative 8 plus 8. And then finally, minus 1 times 10 minus 12. So I'm going to get a negative 2 plus 0 plus 2 equals 0. So because the volume of the parallelepiped formed by those three vectors is 0, all three vectors must then lie in the same plane, and therefore all 4 points lie in the same plane.